what is half-life? Okay, half-life is the time taken, okay, for the concentration of the reactant to fall to half of its original value. Okay, that is going to be half-life. Okay, so like for example, you can measure the half-life, okay, of whenever you have, especially when you have the concentration against time. Okay, that is actually a very good graph. Okay, so that you can calculate the half-life. Okay, so we know that, okay, for concentration against time, okay, we have three graphs. Okay, so I'll just do it again. One like this, one like this, another one like this. Okay, so let it be any kind of graph. Okay, let it be any kind of graph. You should understand, like for example, if your initial concentration is 4, for example, the moment when the concentration become half, okay, which is half of the 4 is 2. Okay, so the time taken for it to become half, okay, the time is going to be, in this case, the time is going to be, they have calculated, is 17. So this is going to be the half-life for this. Okay, but they will actually also calculate, okay, from 2 to become 1. When they do that, they also calculate from here to here what is going to be the value, and they have found out it's actually 17.3. Okay, and then they keep on calculating. Okay, like for example, from 1 to become 5. Okay, from 1 to become 5, what is the time? So the time they found out is 16.7. So roughly what they found out here in this particular graph, they have found out that the half-life is like almost like the same with each other. Yeah, 17, 17.3, 16.7, and so on. Yeah, so they say that a constant half-life, this indicates first order reaction. Now I want you to actually understand about this. We have zero order reaction, we have first order reaction, we have second order reaction. Okay, now if you have a constant half-life, okay, if you have a constant half-life, it is reflecting to the first order reaction. Okay, first order reaction, do remember, okay, first order is going to be a curve. And then you know that the second order reaction, okay, I'll draw using blue ink over here. I told you second order reaction is going to be much more steeper. Okay, let's say I'm just going to draw something like this. Okay, when I draw something like this, okay, what I can see, okay, I'll show you what roughly we can see for the second order. Yeah, from 4, okay, when they become 2, you see roughly the time is going to be somewhere, I'll just roughly take, yeah, maybe 9 minutes. Okay, 9 minutes. From 2, okay, from 2, they become 1. You can see to become 1. You can see there is going to be an increase. Okay, how do I know there is an increase? You can see the distance. Okay, it's definitely more than 9. Okay, definitely more than 9. From 1, when they become 0.5, okay, from 1, they become 0.5, you can see that the distance is actually getting bigger. Okay, unlike the previous one. Okay, it means that for second order, okay, they do have half-life, but the half-life is not constant. Okay, the half-life will increase as the time goes over there. So it means there will be more half-life. It means, yeah, in a simple term, it means second order reactions, okay, they take a longer time for to decompose. If you take it out, they take a longer time to react. For example, it means from 1 to become 0.5 until they become 0. For example, technically, it takes a very long time to decompose. Or let's actually take example for radioactivity. I think half-life is always being used for radioactivity. So of course, when we look at the half-life, we want, let's say, radioactivity to be over, become zero radioactivity. So if you have a big over time, it takes a longer half-life for it to to become half and half and half, it means that that compound, the radioactive compound, will stay in your environment for a very, very long time. Okay, if something that have a very small half-life, okay, short half-life, it means that they will take a shorter time to become zero. It means shorter time to become into safe zone. Yeah, something like that. So again, that's the difference. Okay, there is half-life. Okay, there is half-life, but it's constant for first order only. Okay, for first order only. How about if we have a straight line? Okay, if it is going to be zero order reaction. If I have a straight line, what will happen to my half-life? Okay, from 4 become 2. Okay, this is going to be my value. Okay, from 2 to become 1. Sorry. From 2 to become 1. You can see there is a difference here. Yeah? Okay, let me actually use different pen so that you can actually see the difference. I'll use a red pen here. Okay, from 2, okay, you see they require, okay, from 4 to become 2. This is going to be the half-life. Okay, from 2 to become 1, this is going to be your half-life. From 1 to become 0.5, this is going to be your half-life. From 0.5 to become 0.25, I think maybe somewhere here. What you can notice over here is for zero order, okay, your half-life is going to decrease. You can see from the data itself. Yeah. So the thing is, the half-life is constant only if it is going to be first order reaction. Please actually take note of this. So in summary, if you look over here, okay, this is what I show you just now. Okay, if it is zero order, you can see from the top to come to half, this is going to be a half-life. From here to become to another half, this is going to be a half-life. You can see the half-life is going to actually decrease, okay, for zero order. But for first order, the half-life is going to be the same, constant. Second order, the half-life, okay, is going to be much more, how to say, it's going to, half-life is going to become increasing, okay? It will be a longer half-life from compared to one another, yeah? So here, okay, you can see a zero order has successive half-lives which decrease with time. First order half-life is constant. Second order is going to be successive half-life which increases with time. Okay, so please actually take note of this. So here, okay, I think this one we have covered earlier. Okay, you can see zero order, first order. Okay, but second order, you see it's going to go down, but they will come back up. Okay, it means like, for example, here my graph, this graph is not so accurate because I still need to actually come back up. Okay, so this one is not so accurate. Okay, the one that I draw over here. It's supposed to actually, I hope you understand what I'm trying to say. So this is going to be something like this. So the second graph supposed to be something like this, then go up. Not to be keep on going up, something like this, okay? That is going to be, this is the graph that they want. Okay, this graph. Okay, they will go down and then, okay, the decrease is going to be not so much afterwards. Okay, so please learn how to draw this graph. Okay, so if it is going to be this one, I think it's zero order. Okay, so if you have something like this, okay, this is going to be first order. Okay, second order will be something like this. Okay, they will go like that. Okay, so please refer to your notes on this. Okay, so this half-life, okay, is going to be one of the way, because if you look at the graph that I actually taught you just now, okay, you can always, I think when it comes to rate against concentration, you can decide which one is zero order, which one is second order, which one is first order easily, because all the shapes are different. Yeah. But when it comes to concentration against time, okay, you can only differentiate zero order because zero order is going to be straight line, but it's very difficult to differentiate first order and second order because they are both of them, they are going to be a curve. Okay, so it means this one, take note. Yeah, I told you the graph is going to be slightly coming. If I draw again here, the graph, okay, maybe second order, so this one will be something like this. Okay, so this red graph is going to be for first order. Okay, so take note. Okay, how do I differentiate first order and second order? You can actually find out or differentiate them by using the half-life method. Okay, you need to actually find out what is the half-life, okay, by using the graph. If you can actually identify there is a constant half-life, okay, like previously, they calculate 17, then 16.7, 17.3 is considered to be constant. Yeah, because why the number is not always the same? Because of course, when we draw curve, okay, the number will not be always the same. Yeah, because it's not perfect. So if you have some kind of that pattern, yeah, that is going to consider, we can consider it being first order reaction. So first order reaction, okay, first order reaction will have a constant half-life, but I think the zero order, when the half-life is going to be increasing, okay, let me show you here. If you have, okay, if you have the half-life, yes, zero order half-life is decreasing, second order half-life is increasing. Okay, so if you try to put it in that way, if your half-life is decreasing, then it's zero order. Half-life is increasing, then it's going to be second order. Okay, please try to refer to the half-life. Okay, is there any question up to here?